Today is what, Monday, October 10th? Is that right? I don't remember offhand what's the date scheduled for exam 2. Wednesday of next week, so we've got 9 days here. So today we're doing section 4.2, the mean value theorem. Pretty much the entire lecture is going to be the focus, and applications and other theorems related to the mean value theorem. Wednesday we'll do a little bit in 4.3. We're not going to do the entire section, but we'll do the first 4 pages or so, and we probably will start chapter 5. Section 5.1, and chapter 5 is our toughest chapter about integration, the theory of integration. It's pretty challenging, especially the proofs in the book, to really try to understand those, and to do proofs on your own too. So we'll do section 5.1 a little bit on Wednesday, a lot on Friday. Probably start section 5.2, or at least focus on the main facts from section 5.2 by next Monday or so. And probably your test will include certainly definitions and theorems through section 5.2, and perhaps proofs through section 5.1, or maybe an easier type of proof from section 5.2 will be what your exam will be through chapters 3, 4, and the first couple sections of chapter 5.
So for the study guide for chapter 5, how much should we?
I'll have to figure that out. So if you could send me a note after class to remind me, I'm sure to figure it out. All right, lecture 16, again, our main focus is going to be the mean value theorem. We spent time the very first day of class talking about the mean value theorem. MVT, right? Because you could also call it most valuable theorem, at least for differential calculus. The book even goes so far to say it's sometimes called the fundamental theorem of differential calculus, which is different than the fundamental theorem of calculus. Related to derivatives, it's a pretty obvious sounding fact when you look at its statement. But the proof, when you sort of deconstruct it, as we will do today, does ultimately depend on the completeness axiom. So let's break down the statement of it. Mean value theorem. It's our third value theorem so far, right? We've got the intermediate value theorem, we've got the extreme value theorem, and now we have the mean value theorem. Suppose you've got a function defined in a closed interval, and here I'm going to go ahead and use interval notation like the book does to emphasize that we're defined in some closed interval, and we're going to assume f is continuous on the closed interval. And since this is chapter 4, there must be something about derivatives here, and the next assumption is that you say, and it is differentiable, has a derivative on the open interval. It's sufficient to assume that it's just differentiable on the open interval and not at the endpoints. Perhaps you've got a function that's got a vertical tangent as you approach an endpoint. For example, like the square root function. You consider any closed interval with 0 as the left endpoint, like 0 to 5 or something like that. It is continuous on the entire interval. It fails to be differentiable at 0. It's not even left, or not even right differentiable as a left endpoint. The tangent becomes vertical as you approach that point. That would be one example where the mean value theorem would still apply, even though the function is not differentiable at 0. Another example, actually, where you could fail to be differentiable at both endpoints would be like the arcsine function. The graph of the arcsine function looks like this, and it's got vertical tangents at 1 and -1. So it fails to be even one-sidedly differentiable at those points. I hope you know what the graph of the arcsine function looks like. It looks like that. Why don't you just pass it up instead of going in front?
No, I'm
Okay.
going back.
Okay. Thought you had your homework. Sorry. Here you've got differentiability not on the closed interval, but on the open interval. It's continuous on the closed interval. Again, you've got vertical tangents as you approach either endpoint, but the mean value theorem would still apply to it. So by only assuming differentiability on the open interval, you get a stronger theorem that does apply to these examples too. The conclusion is then there exists a point C in the open interval such that the derivative at C, the derivative of f at C, which will be the slope of the tangent line, of course, right? Don't forget that, is equal to the slope of the secant line between the points A comma f of A and B comma f of B. Drawing a generic picture makes it easy to convince yourself that this is true on an intuitive level. If this is A and this is B, the secant line between the points A comma f of A and B comma f of B looks like that. The mean value theorem says there's some number C between A and B, strictly between A and B. I even made it look like almost a vertical tangent here at A, where the slope of the tangent is the same as the slope of the secant. They'll be parallel. Perhaps right about there is a point where the tangent has a slope that's the same as the slope of the secant. So right about there would be the C that is guaranteed to exist in the conclusion of the mean value theorem. There can be more than one C. Graph looks like that. There's your secant line. There's more than one spot where the slope of the tangent is the same as the slope of the secant. Okay, so there can be more than one C, but there's guaranteed to exist at least one C. So that's the statement. There's a visual emphasizing the geometric meaning. Here are a couple examples emphasizing that you only need differentiability on the open interval. You should also know, as a real basic thing, that if your function fails to be differentiable at even one point, the conclusion might not hold. And the simplest example is the absolute value function. Take it to be on any interval where A is negative and B is positive. For example, the interval from -2 to 7. F of 7 minus f of -2 over 7 minus -2. That'll be 7 minus 2 over 9. 5/9 is the slope of the secant line. Graph looks like a V. Slope of that line is supposed to be 5/9 here. There is no point where the derivative equals 5/9. The derivative equals -1 over here when x is negative, and +1 when x is positive, and it does not exist at 0. F prime of 0 does not exist. Never does the derivative equal 5/9. If you fail to be differentiable at even one point, it's possible that the conclusion will not hold. On the other hand, you should also be aware that the hypotheses might not hold for a certain situation, but the conclusion could hold. That can happen. For example, take the cube root function. On any interval containing 0 in the interior, where the left endpoint is negative and the right endpoint is positive, and I think the conclusion will hold. I think about particular examples here, like consider the interval from -8 to +27. F of 27 minus f of 8 divided by 20, or minus f of -8, excuse me, divided by f 27 minus -8. Cube root of 27 is 3, cube root of -8 is -2. 27 minus -8 will be plus 35. 5/35 or 1/7 is the slope of the secant line. Is there a place where the derivative has a value equal to 1/7, where the slope of the tangent to the original function does have that same slope? I believe it will be true. But there will be a place where that is true, and you can graph it to see that visually. In fact, there might even be two places. There's the derivative. Set it equal to 1/7 and see if you can solve for x. Multiply both sides by 3 to get x to the -2/3 is 3/7. Take the reciprocal of both sides, x to the +2/3 is 7/3. raise both sides to the 3/2 power, and take plus or minus square roots really. Plus or minus 7/3 to the 3/2 power looks like it works. That would be the same as plus or minus 7/3 times the square root of 7/3. You want to double check that those are both between -8 and 27. I'm pretty sure they are. 7/3, yeah, it's about 2, a little bit bigger than 2. Take the square root. Yeah, definitely both of those are in the interval. If you draw a graph, it seems pretty clear that it's true. Remember, the cube root function I said last time fails to be differentiable at 0. We have an infinite tangent there. I should say a vertical tangent. Undefined slope, really. It fails to be differentiable at 0, but there are points where the slope of the tangent equals the slope of the secant. Right about here and right about there. It's not drawn very well. Those points actually should be equal distance from x equals 0, but I didn't draw it that way. So you get the main points here? This is a theorem. We are going to prove it. Here's the intuition by why it seems plausible, but not a proof. It's good to consider even the simplest example, the absolute value function, fails to be differentiable at one point. On any interval where a is negative and b is positive, the conclusion of the mean value theorem will not hold. But there are examples, like this one, where even though the hypotheses do not hold, the conclusion still does. That can happen for specific examples. There's just no guarantee from the theorem. How do you prove the theorem? Well, again, we're going to deconstruct it here. We're going to go backwards, so to speak. Although the first step in this backwards kind of approach to the proof, I don't know the best way to describe it. It might seem a little funny or artificial or something like that. We're going to use something called Rolle's theorem to prove it. And Rolle's theorem, it's kind of interesting, is actually a special case of the mean value theorem. And so then the crux of the matter will then be proving Rolle's theorem. Rolle's theorem says, suppose you've got a function in the same kind of situation that is continuous on the closed interval and differentiable on the open interval, and suppose f of a equals f of b. The conclusion is then there exists a c between a and b such that what happens? Well, if the function values are the same, that means the slope of the secant must be 0. There must be a c where f prime of c is 0, where the tangent has a slope of 0. It's a simpler looking conclusion, but it does follow from the mean value theorem. We can easily prove Rolle's theorem from the mean value theorem. What's not so obvious and what's pretty interesting is you can actually take this special case of the mean value theorem and prove the more general case. Once you see the trick, it's actually pretty easy, though it does involve, Travis, a trick. Okay.
I love it.
You love tricks?
Yeah.
All right, these are all good tricks to know and to learn about and to try to remember. But then the harder work will be proving Rolle's theorem. So we are, in a sense, by using Rolle's theorem to prove the mean value theorem, we're avoiding the hard work for the moment. Proof, sketch. I'm just going to do sketches of the mean value theorem. Proof sketch, PF there. For sake of time, we've got lots to talk about today. It's a little trick, yeah. Well, or maybe you'd call it a big trick. Actually, maybe we should have the picture back up here. It's kind of similar to the trick that you use to prove that a function that maps an interval into itself and is continuous has a fixed point. You took the function minus x to create a new function that you apply the intermediate value theorem to. It's a similar trick here. If this is the graph of f, and we've got a secant line here between the endpoints, that's the graph of some function, a linear function. Maybe, well, if I subtract that linear function from f, I get a function whose values at a and b would be the same, because these two graphs come together at the endpoints. And if the values of that new function a and b are the same, I could apply Rolle's theorem to it. And maybe that application of Rolle's theorem to that new function would get us what we want, maybe. It's not obvious that it will, but maybe if we're lucky here. Let g of x be f of x minus L of x, where L of x is a function whose graph is this secant line. Stylistically, I should really say what L of x is first, but oh well. What is L of x? How would you make a line whose graph is this? You got to get the slope right, and you got to get a point right. You know the slope, you know a point, you can get the formula right, but we are doing it in an abstract form. We don't have specific numbers here. The slope of that line will be that. That's the slope of the secant line. It has to get multiplied by x in the equation for this linear function, so that it is the slope of that linear function. You could also multiply it by x minus a, and it would still have the right slope. The benefit of writing x minus a, though, is that it helps me guarantee that I get the right point, this point on the graph of L of x. If I just now add f of a to this, that will do it. This quantity, this quotient there, that's the slope of a secant line. It's an average rate of change. It's being multiplied by x, so it is the slope of this linear function. And if you plug in the point whose x coordinate is a into here, you get 0 plus f of a. 0 plus f of a does give you f of a. That does go through the right point. It's certainly differentiable. It's a linear function. We know we can differentiate it. We know, well, okay, let's check. Does g of a equal g of b? We're going to apply Rolle's theorem to this new function g, which I was trying to say before that is going to be continuous on the closed interval and differentiable in the open interval, because f is, and certainly because L is. What is g of a? Well, I already talked about what you get when you plug in a into L. You get 0 there, plus f of a. You get f of a. We're subtracting it. G of a is 0. What about g of b? It's less clear that g of b is going to be 0, but it will be. You'll get f of b minus, in parentheses here, f of b minus f of a divided by b minus a times b minus a plus f of a. The b minus a is canceled there. Inside the parentheses here, the f of a's cancel. You ultimately get f of b minus f of b. You get 0. Got that? Right, just replacing x first with a to get that, then with b to get this. Divide those out. In the parentheses here, cancel the f of a. We got a minus f of a there and a plus f of a. Then ultimately we just have f of b minus f of b, which is still 0. So for g, there must be some c between a and b where g prime of c equals 0. The only thing left you can figure out then is, does that mean this is true? How do you relate that to f? Well, you can relate the derivative of g to the derivative of f. G prime of x will be f prime of x minus L prime of x. But L prime of x is easy. It's a linear function. Its derivative is its slope. It's a constant function. F of b minus f of a over b minus a. So by saying g prime of c equals 0, from Rolle's theorem, g prime of c will be 0. That means at c, this will be 0. And I hope you can see it in your mind's eye without me writing it down. That would imply that this is true at that value of c. Should I go through it quick again? Okay, it's a trick. It's an ingenious trick to use the special case of the theorem to prove the theorem itself. Create a new function. That's the original function minus a function that's linear, where the graph of that linear function is this secant line. Actually, I could get away with using any other parallel line too. Using the secant line ultimately allowed me to say g of a and g of b were 0. What is the formula for that linear function? That does work. It's got the right slope. It goes to the right point. That's the main trick right there. Then there's this wondering, if we apply Rolle's theorem to g, will we get the right conclusion? And fortunately we do. You've got to check that the hypotheses of the Rolle's theorem applies to g. G is going to be differentiable in the closed interval and continuous in the closed interval and differentiable in the open interval, because f is assumed to be, and certainly linear functions definitely are everywhere, continuous and differentiable. Check that g of a and g of b are equal. They are. They're both 0. Therefore, by Rolle's theorem, there is a c between a and b, so that g prime of c is 0, because I'm applying Rolle's theorem to g. Because g prime and f prime are related, that means something about f prime as well. It means f prime of c minus this is 0, which means this is true. Okay, but this is begging the question then. How do you prove Rolle's theorem? Sketch of proof of Rolle's theorem. It requires another theorem, continuing to work backwards, that your book doesn't give a name to. I've seen it called Fermat's theorem before. Fermat. That's not the same as Fermat's little theorem from algebraic structures. It's also not the same as Fermat's last theorem, which was proved some 25 years ago, 21 years ago. I think it's when they finally had an airtight proof, which the person who proved it became world famous. Okay, it was in the newspapers everywhere. They made a Nova video about him. His name is Andrew Wiles. Anyway, this Fermat's theorem is different than those. It says that if you've got a function that's got a local max or min at an interior point of an interval, and if the function is differentiable there, the derivative must be 0 at the max or min. The derivative must be 0 there. Let's sketch the proof then. So again, we're trying to prove Rolle's theorem. So we are assuming we've got a function that's continuous in the closed interval and differentiable in the open interval. If the function's constant over the interval, if f of x equals f of a for all x in the interval, including at b where you're already assuming f of a equals f of b, then the conclusion is obvious. The function's a constant function, its graph is horizontal, its derivative is always 0, including at every interior point of the closed interval. Then the conclusion is trivial. right? Getting that? Because f prime of c will always equal 0 for all c between a and b. I am assuming a is strictly less than b here. If not, if this is not true, then the function by the extreme value theorem over this closed interval will have a global max and min somewhere, a global extreme value, which will also be a local extreme value. And by Fermat's theorem, that means where you have the extreme values, f prime of c will be 0. So actually, that doesn't feel like much of a proof either, but it does prove it. There exists a C and AB where f has either a global max or global min, so it's a local max or a local min as well. Our book doesn't really use the word global anywhere. I like using it. They just say extreme value, max or min. They avoid the word local, but they use a different word. They say relative. The author, I should say, does. I like using the words global and local for emphasis. Global is over the entire domain. Local means nearby some point, in some neighborhood of the point. That's the EVT, really. By the EVT, extreme value theorem. And then by Fermat's theorem, not Fermat's little theorem, not Fermat's last theorem, and the book doesn't call it Fermat's theorem. I will point it out to you here. It's at the beginning of section 4.2, it's theorem 4.10, page 139. That's what I'm calling Fermat's theorem. Since the function is differentiable there as well, f prime of c must be 0. The book states the conclusion of Fermat's theorem as either f is not differentiable at c if you've got a local max or min there, or f prime of c is 0. In either case, you've got a critical point for the function at c. Yeah, they use the word relative extreme value. Local max or local min is another way to phrase that. They don't assume f is differentiable at c, so they say either f is not differentiable at c or f prime of c is 0. But we're in a situation here where f is differentiable on the open interval in the assumption of Rolle's theorem. And therefore, we don't have to say, well, maybe f is not differentiable at c. It is. And f prime of c must be 0. So actually, that proof is not too bad once you see that kind of trick. Which again brings us back in our deconstruction of the proof to, well, how do you prove Fermat's theorem? Sketch of proof of Fermat. I think calling it Fermat's theorem is not completely standard. Maybe that's why our book didn't call it that, but I've heard some people call it Fermat's theorem. And I'm pretty sure I do remember hearing or reading that Fermat did work on differential calculus. He was before Newton and Leibniz, and so he didn't have the fundamental calculus to connect integrals and derivatives, but he did work on slopes of tangents and calculating those slopes before Newton and Leibniz came up with the full-fledged calculus. Essentially, you got to think about this kind of difference quotient here carefully. This is a real sketch. Okay. Mostly I'm just writing this and I'm going to think about it here. Okay. So what are we assuming with Fermat's theorem? If we assume the function is differentiable at c, where you've got a local max or min. You can look at the statement of Fermat's theorem if it helps. Page 139. You've got an interval, a function defined in the closed interval. You've got an interior point, not an endpoint C, where you've got a local max or min, high point or low point, not necessarily global, but local. Then the f is either not differentiable there or f prime of c is 0. You can prove that by saying, well, let's say f is differentiable at c, because otherwise the conclusion is obvious. It would not be differentiable at c. So you can say, okay, assume f is differentiable at c and prove f prime of c is 0. Essentially, it's just thinking about this difference quotient as x approaches c from the right or the left, and thinking about the fact that f has a local max or min at c, say a local max, just for sake of completeness here. If x is bigger than c, then x minus c is positive, greater than 0, and f of x minus f of c, if f of c is a local max, that can't be positive. Could be 0. That's less than or equal to 0 when x is bigger than c. Actually, also when x is less than c, but when x is bigger than c, the bottom is positive. Making this fraction as a whole less than or equal to 0, not only for fixed x greater than c, but also as x approaches c in the limit. So the right-hand limit as x approaches c from the right here must be less than or equal to 0. Because when x is bigger than c, the bottom is positive. And because you got a local max at c, the top is less than or equal to 0. Can't be positive. Makes the whole fraction non-positive, and the limit then must be non-positive. On the other hand, if you let x approach c from the left, the top is still less than or equal to 0, but the bottom is now negative, making the fraction as a whole greater than or equal to 0 for any fixed x less than c now. The slope of the secant is positive, or at least not negative, and therefore in the limit it's got to be greater than or equal to 0. Non-strict inequalities are preserved by limits. Just a second. If I'm assuming f is differentiable of c, that means these two limits must be the same. The one-sided limit must equal the one-sided limits must equal the two-sided limit. Since this one's less than or equal to 0 and this one's greater than or equal to 0, they must both be 0, and the two-sided limit must be 0. F prime of c must be 0. Travis?
So how would you do this with like a x squared function?
You mean with a local min instead of a local max?
Yeah, like where would
Instead of this
your-
picture, you got this